In this video, we're going to examine the relationship between thickness and vertical structure of systems. Here we have a schematic where geopotential height increases upwards, where the pole is towards the left of the diagram and the equator is towards the right. And there's a gradient in temperature or thickness from south to north. So it's a southern hemisphere picture, with cold air to the left and warm air to the right. We can see under this situation that the pressure surfaces slope upwards, so they're closer together in the cold air and further apart in the warm air. If you think about the way in which thickness is constructed, to go from one pressure surface to another, in the colder air mass the density is lower, and so you have to integrate through a smaller depth of atmosphere, thinking about the hydrostatic equation, to get to the next pressure level. Whereas in the warmer air the density is smaller, and so you have to integrate through a larger depth of atmosphere, thinking about the hydrostatic equation, to get to the same pressure value. So from cold air to warm air, the pressure surfaces slope upwards, and typically what we see is that pressure surfaces slope upwards towards the tropics. Now let's think about the relationship between thickness and the thermal wind and the vertical extent of systems. You recall from dynamic subject that the thermal wind equation has the following components, that UG dz is minus G on F naught T dt dy, and dVg dz is equal to G on F naught T dt dx. Remembering that the thermal wind is simply the geostrophic wind shear for a layer. It's not actually a physical wind, it's just a wind shear. Schematically, you can see on the right a lower level geostrophic wind and then an upper level geostrophic wind, and if you add the thermal wind to that, to the lower wind, you get the upper wind. So the thermal wind is just a shear in the geostrophic wind. In the southern hemisphere, the thermal wind blows parallel to mean isotherms for a layer with the cold air to the right. So let's apply that. So here we have a case where there's a temperature gradient from south to north, or from pole to equator in the southern hemisphere. What's illustrated in the shading is the layer temperature gradient. So the thermal wind runs parallel to these mean isotherms with the cold air to the right. And so in the southern hemisphere, the thermal wind is a westerly. It turns out that the same thing happens in the northern hemisphere because the thermal wind blows with the cold air to the left. Now let's look at the vertical structure of systems. In this same equatorward temperature gradient, with a closed low at the surface, we add an increasingly westerly component with height, that is the thermal wind, or the shear in the geostrophic wind. So if you add a constant westerly wind to a closed low at the surface, in the mid-levels you end up with a mid-level trough. So you're reinforcing the westerly wind, which is equatorward of the low centre, and weakening the easterly wind, which is poleward of the low centre. And so the closed low circulation opens out into a trough. And then finally, further and further up, you get an upper level westerly wind, or a westerly jet. At some point in the atmosphere, the temperature gradient reverses, and so that westerly component weakens. So it reaches a maximum at some height in the atmosphere, which we refer to as the jet core. Now let's consider a warm cored low pressure system in the southern hemisphere, and that's represented schematically here. So warm cored means that at the center of the low is the warmest air, and that the temperature decreases outwards from that. We have a low pressure system because you can see the surfaces of pressure sloping downwards towards the center of the low. So if one were to move from west to east along the surface, you would encounter lower and lower values of pressure until you reach the center of the low, which would be a minimum, and then as you moved outwards the pressure would increase again. You can see at the surface that the low pressure system in the southern hemisphere is associated with clockwise winds, with a northerly wind on the eastern flank of the low and a southerly wind on the western flank of the low. Now consider the thermal wind equation, that is the shear and the geostrophic wind, for the meridional component of the wind as it changes with height, dVg dz. That's equal to G on F naught T dt dx. In the southern hemisphere, F naught is less than 0. On the western flank of the low, we see that as we move in the negative x direction, the temperature decreases. So a negative change in temperature divided through by a negative change in the zonal direction gives us dt dx is positive. and F0 is negative, so that the sign of the term on the right hand side is negative. So dVg dz is less than 0, and hence Vg decreases with height. We define a southerly as positive, and so on the western flank of the low, the southerly weakens with height and eventually becomes a northerly wind. Now looking on the eastern side of this low pressure system, we see that the temperature decreases in the increasing x direction. So del T is negative, where del X is positive, so partial dt dx is less than 0, and because F0 is less than 0, the magnitude of the term on the right hand side is positive. So dVg dz is greater than 0. At the surface we have a northerly, and because dVg dz is greater than 0, it means that northerly weakens with height, and eventually we establish a southerly. So due to the thermal wind, we can see that we go from a clockwise rotation, or a cyclonic rotation at the surface, to an anticyclonic or an anti-clockwise rotation aloft. Now this coincides eventually with a high aloft, and we can think about that in terms of the thickness. For large values of temperature, we have large values of thickness, which means the distance between two pressure levels is larger over the warm air than it is over the cold air, which means that eventually surfaces of constant pressure must bow up over the surface low. In other words, we move from a low in pressure near the surface to a high in geopotential aloft, which coincides with the anticyclonic winds. Looking at the real atmosphere, here we have the monsoon trough in terms of a streamline analysis, and so the trough is marked in as the dot-dashed line as the axis of minimum surface pressure, but also the axis of maximum cyclonic vorticity or cyclonic rotation in the winds. All of these lows are going to be warm cored, and so when we look at the 500 hectopascal wind field, we can see that the low in the Coral Sea and the low in the Indian Ocean have given way to anticyclonic rotations. However, the low over northern Australia is still present. So in most cases, the warm cored low will result in an anticyclonic flow at 500 hectopascals and aloft. What about a cold cored low? Stop the video at this point and do the same calculation as we did for the warm cored low, evaluating the terms in the thermal wind and seeing what results. Well, how did you go? You should have found that we'd have the opposite case, and that the cyclonic winds build with height. This is illustrated well in this real example. So let's consider the low over Victoria. There's a low over Victoria in the mean sea level pressure, and so it has cyclonic winds. And then to the west you can see a thermal trough represented by the thickness pattern. Associated with that, by argument of the thermal wind, is a cyclonic rotation in the winds. So the system tilts towards the cold air with height, that is, the pressure surfaces slope towards cold air, they slope upwards, but the winds are also cyclonic. We can also see that with the low pressure system in the Southern Ocean there. There's a low of 994.5 hectopascals with associated cyclonic winds, and then the thickness trough tilts towards the west with height, again with the associated cyclonic winds. So cold cored lows have deep vertical extent, and their slope with height depends upon the distribution of the cold air. Now let's consider cyclones and thickness patterns, which we touched upon a little bit before. So in the top figure we have a warm cored low, and you can see that that means at the surface we have those cyclonically rotating winds, and the thermal wind tells us that those winds will weaken with height to produce an anticyclonic circulation. But likewise, because the warm air has lower density, we have to integrate through a deeper depth of atmosphere in order to get to a given pressure level than we would for a colder air mass. And so that means that pressure surfaces bow up above warm air. So we move from a low value of pressure near the surface, a pressure low, to a geopotential high, which is consistent with the idea of the winds moving from cyclonic at the surface to anticyclonic with height. Compare and contrast that to a cold chord low, where the thermal wind tells us that the cyclonic winds should strengthen with height. In the cold air, considering the hydrostatic equation, we have to integrate through a smaller depth of atmosphere to get to a certain value of pressure. Or thinking about the hypsometric equation, there's a lower thickness value. So a smaller distance between pressure levels in the cold air. What that actually means in this situation is that there's an increasing pressure gradient or an increasing geopotential gradient with height, which also shows us that the cyclonic winds should strengthen with height. In terms of anticyclones, we can see for a cold chord high, the argument runs the same way. We should move from anticyclonic winds at the surface to cyclonic winds aloft, firstly moving through a region where the winds are equal to 0. So that's the thermal wind argument. What about the thickness argument? Well, in the cold air, the thickness values are small, which means that the geopotential gradient weakens with height. And the geopotential gradient, of course, is related to the strength of the geostrophic wind. Whereas for a warm chord high, we can see that, firstly, from the thermal wind argument, the thermal wind is in the same direction as the surface the surface geostrophic wind, and so the anticyclonic winds strengthen with height. But in terms of the thickness, in the warm air, the thickness is large, which means the geopotential gradient increases with height, and hence the geopotential gradient force and the geostrophic wind strength. So the thickness patterns and the thermal wind arguments are in agreement with each other. Now let's look at a chart overall, and we can see a number of things. Over northwestern Australia, you can see a low pressure system, which is the heat low, and it's associated with high values of thickness. So what should happen to that low with height? Well, as we've seen, the thermal wind will be in the opposite direction to the geostrophic wind, so the geostrophic winds will weaken with height. Likewise, the geopotential surfaces will bow up with height, and so we'll move from a low or a dip in the pressure surfaces to a flat surface and then a dip upwards. So with height, we should go from a low to no particular gradient in the geopotential to a high aloft, and the winds go from cyclonic to 0 to anticyclonic. The trough or front in the Southern Ocean, you can see marked in the blue dashed line, has lagging to the west a thickness trough. And so what we should see is a tilt of the low pressure surfaces with height and the consequent wind structure as well. So there'll be cyclonic winds aloft, but the whole pattern will be tilted towards the west. What about the tropical cyclone? That's an interesting case because tropical cyclones are warm chord, but they're warm chord all the way to the tropopause. So this might look something different to the warm chord low over Australia. So here's how the pattern changes with height. We've got 850 hectopascals top left, 700 hectopascals top right, 500 hectopascals bottom left, and 200 hectopascals bottom right. And we'll approximate the tropopause by about 200 hectopascals. You can see that the heat low is still evident at 850, but gives rise to a high at 700, as we expected. A warm chord low is shallow, and via thermal wind arguments, the winds will shift around from cyclonic to anticyclonic, and that, of course, is the case for the high. And then that high shifts towards the north, towards the warm air with height. You can see that the trough in the Southern Ocean moves slightly towards the west with height, but you'll also see, because there's a north-south orientation to the thickness pattern, that the geostrophic winds have built with height, and so you can see a jet on the western flank of that trough there at 200 hectopascals of winds 100 knots or more. Likewise, because there's a north-south temperature gradient over southern Australia, there's a weaker jet there in the bight. And as noted, because the tropical cyclone is warm cored all the way up in the atmosphere, you see a persistent cyclonic rotation right up until just below 200 hectopascals. And so the cyclonic winds and a low pressure system, or a low geopotential system with height. So let's go back to our initial MSLP/thickness chart. You can see, as we talked about for the heat low, because it's warm cored, it gives rise to a high aloft. Because the thickness pattern lags the front or the trough in the Southern Ocean, we see that the trough itself will lag back towards the west. Because there's a strong barocline with a north-south orientation behind the surface front, that's where the jet will be, and you can see associated with the high, or to the north of the high in the bight, a north-south thickness gradient, again associated with the temperature gradient, which gives rise to the jet via the thermal wind argument. And then you can see the tropical cyclone, which, as we've noted, retains its cyclonic nature with height.